Sounds good. All right. All right, hello everyone. For those of you who don't know me, my name is Robbie. I'm a solutions architect with NVIDIA. Today we're going to be talking about concurrency with multi-threading. This is a question that I get asked a lot by popular demand. We're going to dive into it today. So it's important to note that we'll just define our terms up front. When I talk about concurrent scheduling, I'm talking about processes running on the GPU simultaneously. The onus is on the user to create and manage scheduling streams. The default scheduling behavior on a GPU, if you have multiple processes submitting kernels to a GPU, is that the processes will share the GPU through time slicing, and the scheduling is managed by the system. You can control that time slice with our NVIDIA SMI tool, but this is sort of not our goal today. Today, we want to be executing concurrently. So when I talk about concurrent scheduling, this is what I'm referring to. And I wanted to give a brief sort of review of CUDA streams. So if you were with us for the CUDA training series last year, module, I think it was 7, talked about just how to use CUDA streams generally. So this will be a little bit of a review. But for those of you who are not with us for that, I figured I'd go over the basics of CUDA streams, and then we can talk about how CUDA streams behave in a multi-threaded context. So some basic semantics of CUDA streams. 2 operations issued in the same stream are going to execute in issue order. So what that means is if I have 2 operations, operation A and operation B issued after operation A into that stream will not begin to execute until operation A has completed. However, if we issue these operations into separate streams, there's no notion of ordering prescribed by CUDA. So it's possible that operation A may execute before, during, or after operation B, as long as they are issued in different streams. Typically, what is an operation? An operation is usually either some kind of memory memcopy operation, or it's a kernel call. More generally, there are CUDA API calls that take a stream parameter as well as stream callbacks, and there's an optional stream parameter for any kernel call for a kernel that you've written yourself. And just to give an example of what that would look like, this is a basic sort of stream creation and compute copy overlap. So we have streams 1 and 2 that we've created, and we have a memcopy async operation here. So we're going to copy some data over to the GPU on stream 1, and then we have a kernel that we are launching on stream 2. And then we have if you see that this CUDA stream synchronize on stream 2, basically what we're saying is we want our CPU thread to wait on whatever instructions were issued into stream 2. In this case, it's a single kernel call, but kernel calls are non-blocking with respect to the CPU thread. So it's just important to note that. It's also worth noting that because there's no notion of ordering for this memcopy call and this kernel call, you would not want to do this if any of the memory being copied over in this memcopy call is required for the kernel computation. This is something where these 2 things, in theory, are completely divorced from one another. A more concrete example of this would be a vector math operation. So this is actually kind of similar to our homework code, which is based off of the solution from homework 7, which basically takes a vector math operation where we have an array and we have some vector math kernel that we launch on that array, and we chunk it up. And basically we want to overlap some of the host to device mem copying with our actual vector math computation. So we don't have to wait for the entire array to be copied over to the GPU in order to begin our kernel execution. So in this case, in this example, we just have 2 streams that we're sort of oscillating back and forth between. And on each stream, we're doing our host to device copy followed by a kernel call for that particular chunk of memory, and then our device to host copy for the results. And the way this would execute is basically you have on stream 0, your first hosted device copy, your first kernel call, and your first device to host copy for your results. Then on stream 1, you have your next chunk of the array, host to device copy, kernel, and device to host copy. And within each stream, these operations will execute in issue order, but stream 0 and stream 1 do not have any sort of notion of ordering. So it's just important to make sure that within each stream, you're copying the corresponding chunk of the array over to the GPU before you actually begin processing that particular chunk of the array. And this is kind of just a small exercise example, but there are plenty of code bases where you have maybe not a chunked array necessarily, but just 2 entirely different arrays, and you're already performing computation on one of those arrays, and you want to sort of get the next array ready for the next kernel that you have to launch. You can use streams to do that sort of thing. If you don't specify a stream, however, things will launch in the default stream. So for anyone who's never used streams before, you've probably been using the default stream the whole time. Kernels or CUDA memcopy calls that don't specify a stream use the default stream. So the legacy default stream behavior is that it actually blocks on the entire device, the whole GPU. So even if you had stuff running in other streams, if you then submit work to the default stream, it's going to actually block, it's going to wait on all of the other streams to complete execution. It's going to then execute whatever you submitted to the default stream, and then anything that was issued into other streams in the meantime during that default stream execution will still be blocked from beginning execution until whatever the work item from the default stream is completes, if that makes sense. So all host threads share the same default stream on a GPU. And basically, we just want to avoid using this during complex concurrency scenarios. But this sometimes can become a point of confusion where you launch one work item, and then for your second work item, you create a stream thinking, well, like, okay, the first one by default will execute in a different stream, right? It's like, well, actually, no, that'll execute in the default stream and you won't get any concurrency there. So if you want concurrently executing work items on the GPU, you will have to create a stream for each one. This behavior can be modified to convert it to an ordinary stream. So without this special behavior, by using the -- default stream per thread flag when you compile your application with MVCC. And in that case, each host thread will get its own ordinary default stream that won't block on the entire device. So other use cases for concurrency, host device execution concurrency. So if we have a kernel and we don't want to block on that kernel, we just want our CPU host code to continue execution, because presumably at that point in time, we don't yet need the result of that kernel. We can do that, or we can launch concurrent kernels. So we can have 2 different streams, and instead of using a CUDA memcopy operation and a kernel, we can just use 2 kernels. One in stream A and one in stream B in this case. And the reason that you'll see all of my slides throughout this presentation say these kernels have the possibility to execute concurrently. They won't necessarily execute concurrently. One won't necessarily execute before or after the other one. It's actually pretty hard to witness concurrent kernel execution on the same device, because it requires kernels with low resource utilization but long execution time in that limited amount of hardware resource utilization. So what that means basically is if I have 2 pretty big kernels that do a good job saturating the GPU on their own, and I launch them in different streams, they have the possibility to execute concurrently. But what will happen in practice is one of them most likely will begin execution and suck up a bunch of the GPU hardware resources so that there are none free for the second kernel. And as it completes execution, the first kernel completes execution and starts freeing up those resources, you'll see a little bit of overlap where the second kernel will come in. If you look at your profiler output, you'll see a little bit of overlap toward the end. But you might be thinking to yourself, shoot, like I thought that these were going to execute at the same time, and it doesn't look like they're doing that. It looks like they're doing that only for sort of a split second or so. And that's normal. It's because one of your kernels is saturating the whole GPU. So there's no benefit or no reason for them to be executing concurrently. So I just want to point that out, that with streams, you're not necessarily forcing anything to execute concurrently. You're just giving the ability to execute concurrently if one of those kernels does not actually utilize all of the resources that are available on the device. It is worth noting that this is less efficient than saturating the device with a single kernel. So if I have two smaller kernels that have low resource utilization but a long execution time, so I schedule them on different streams and they execute concurrently, it's still less efficient than saturating the device with a single kernel. There's still kernel overhead there's still overhead with respect to kernel launches. So it's still, if we can, we still want to use a single kernel. It's just that that's not always feasible depending upon our code base. Now, all of that said, that's just kind of a review from homework from Lab 7. How does this sort of fit into the greater picture of multi-threading and, in our case, HPC applications? Well, HPC applications typically, run on HPC applications, at least that are running on systems like Summit or Cori or Perlmutter, excuse me, typically use MPI to decompose their applications across nodes. And then some applications just use pure MPI parallelism for the CPU side of things, and that's okay. And in that case, you can, the multi-threading component of this lecture is probably not relevant, but a lot of legacy HPC codes like to use OpenMP for their on-node shared memory multiprocessing. But then now GPUs came along and they want to now sort of update their applications to add GPUs into the mix. Well, they're faced with the decision here, which is either, do I rewrite my entire application to basically eliminate the OpenMP portion of my application, or can I, is there a way that I can sort of submit multiple kernels from basically a kernel or more than one kernel from each one of my OpenMP threads onto a GPU, or in the case of a machine like Summit, my 6 GPUs that are available on a given node? And the answer is actually yes. So typically the way that an application like that would look would be, you have your MPI domain decomposition that splits work across the different nodes in the cluster that you're using. Then you have your on-node parallelism with OpenMP, and you're not simply parallelizing one or two small for loops. You're saying, no, I'm going to actually launch a bunch of OpenMP threads to do all of the work that is given to a particular node. But that might require, many different operations that are going on across sort of many different work items or pieces of data within each OpenMP thread. So they might still have a significant amount of work inside of each one of these threads. So rather than rewriting our entire legacy code here, we can use CUDA streams to allow these different OpenMP threads to submit kernels for concurrent execution on a single GPU, or actually on more than one GPU. This wasn't possible before our revision 465 driver, but ever since our R470 driver, which is our newest driver, and CUDA 11.4, this is officially supported. This is a question that I've been getting pretty much since I started here at NVIDIA. So it is something that we officially support now. And just an example of what this would look like, if my slide will switch. Basically, we can create a number of streams, so kind of like our previous example. And then instead of just submitting kernels from a CPU host thread to the different streams, we can have an OpenMP parallel loop submit kernels across all of these streams that we have now created. In this particular example, we have num streams is how many streams we have, and then all we're saying is for our OpenMP parallel for loop, we're just doing I modulo the number of streams to assign each work item to a different stream. And like I said, this is worth it if every thread has enough work to offset kernel launch overhead. So it's kind of a little bit of a dance of finding that balance where, okay, each individual kernel doesn't have enough work to saturate the GPU on its own. That would be the ideal situation. But we also want to make sure that we're not in a situation where we've decomposed our application too much to where each one of these kernels only has a couple of work items. And in fact, we're actually going to get a slowdown just because we're not even offsetting our overhead required to launch those kernels on the GPU. The main benefit of this, of doing something like this, is it requires less programmer overhead than rewriting an entire code base. Ideally, for ideal performance, you would rewrite your entire code base to submit one big kernel to each one of the available GPUs, i.e. removing OpenMP completely and replacing it with CUDA. But this isn't always feasible. I mean, some of these applications are huge. So it is less efficient than saturating a device with streams from a single thread, because you now have multiple CPU threads submitting to sometimes the same stream, sometimes different streams. And it's also less efficient than saturating the device with a single kernel. As I've mentioned before, that's kind of the ideal case. We can use this to also spread work across our multiple GPUs too. So going back to the example of sort of at a high level what a legacy code would look like, where you have your MPI domain decomposition across nodes, and then your OpenMP on-node parallelism to parallelize sort of the whatever chunk of the domain's work was given to that particular node. In modern HPC systems, we don't just have one GPU, we have several GPUs. So what we now have is we have CPU parallelism across all of our available CPU cores, but we have more than one GPU. So we don't want to actually just submit work to one GPU. We might get to the point of saturating that GPU. We might get to the point of oversaturating that GPU and not utilizing our other GPUs in the system. Fortunately, with CUDA streams, we can still do this. We can have our multiple OpenMP threads and spread work across multiple GPUs. It's a little bit trickier, but the main thing to be aware of is that streams have an implicit device association. So when you create a CUDA stream, it is associated with whatever the active CUDA device is at that point in time. So what that looks like in this example here is we have CUDA set device 0. So we're saying, okay, set my active GPU to GPU number 0 and create a stream, which we called stream 0 in this case, which is now associated with device 0. So now it's important that if we try to launch a kernel and assign it to stream 0, we have to make sure that our active device is set as device 0 during that point in time when we actually try to make that kernel launch. So in this example, we've set our device to device 0. We've created a stream called stream 0, which is associated with device 0. Then we've set our CUDA device to device 1. We've created a stream called stream 1 associated with device 1 implicitly, because that's our active device. Now we launch a kernel and we assign it to stream 1. Now we already had our device set as device 1, so that's fine. But now we have to do a second CUDA set device 0 call, because we want to now issue our second kernel to stream 0, and we can only do that if our active device is the one that stream 0 is associated with upon its creation. Kernel launches will fail if issued into a stream not associated with the current device. Cannot do that. CUDA stream wait event can synchronize streams belonging to separate devices, and CUDA event query can test if an event is complete. So those are useful tools for synchronization sake. And how this sort of fits into our bigger picture of multi-threading and CUDA concurrency, it would look something like this. And in this case, we have a number of streams that we create, and then we have our OpenMP parallel for loop. So presumably this would be, sort of a big loop that would have a bunch of different pieces of computation inside of it for our on-node CPU parallelism. And then for this particular use case, I mean, this is just an example for one of the presumably many kernels that would exist inside of this big OpenMP parallel for loop. We have a stream number so at first we decide which stream we're going to be submitting a kernel to, and where in this case, I'm saying J equals my I modulo number of streams. So I'm basically doing a round robin over the streams and the loop iteration. I set my device to J modulo the number of GPUs. So I'm walking through all of the GPUs in my system on my node. I'm doing a stream create. So that stream J is now associated with the device J modulo number of GPUs. And then I'm launching my kernel on that stream. So in this case, we'll have execution across both threads, streams, and GPUs. Multiple threads submitting kernels across a number of streams distributed across available GPUs. An example of what that would look like if we had hypothetically 16 OpenMP threads, 64 streams, and 8 available GPUs, and let's say our N bound was 1024, that would give us 8 streams per GPU because we have 64 streams and 8 GPUs, and then 16 kernels per stream because we have 1024 work items and we have 64 streams. So we're submitting 1024 kernels across those 64 streams. It's worth noting we should have at least 1 stream per GPU, of course, but more will be optimal in a use case like this. You're going to need as many streams on a GPU as it takes concurrent kernels to saturate that GPU, but you want to, if you can figure out for your particular application what the optimal number of streams is, you want that to be the lowest number of streams possible, basically, because the more streams you have, the more concurrent kernel launches you have, which means the more overhead you're going to have. So again, it's that song and dance between figuring out, okay, I know I need more than 1 stream to saturate this GPU because each kernel is not saturating the GPU on its own, but I also don't want to sort of decompose too much and have too many streams where I'm getting killed with kernel launch overhead. So to show some examples of what this would look like in practice, this is a profile from the solution to homework 7, which is actually going to be our starting point today during our lab exercise. This is a single CPU thread submitting kernels across 8 CUDA streams. And we can see there's a lot of concurrent kernel execution here. There's concurrent data transfer and kernel execution here throughout our profile. If I move over to, this is the same example now, but with 8 CPU threads. And unfortunately, so we do support, CPU multi-threading with CUDA streams, but our profiler unfortunately needs to be updated still, because when you turn the profiler on, there are some back-end components of the profiler that require some CPU serialization, unfortunately. So this profile looks kind of whacked out. If I actually turn the profiler off this is the solution to today's lab exercise. If I turn our profiler off, my runtime looks something like this. So single thread default stream, so just 1 single CPU thread, default stream, 1 kernel. My runtime is 0.018 seconds. Single thread plus 8 CUDA streams. So that first profiling example that I showed, we see about a 2x speed up over just using a single thread and just the default stream submitting 1 big kernel for this particular example application. 8 OpenMP threads with 8 CUDA streams without the profiler gives me about the same runtime as the single thread plus 8 CUDA streams, which is what I would expect. In this case, we're not actually getting any speed up out of using the OpenMP threads. This is just an exercise to show you that you can submit kernels across multiple streams on a single GPU using OpenMP. But then as soon as I turn the profiler on, I go back to basically my single thread default stream runtime by coincidence. It could actually be even slower than this because of that serialization when using the profiler. So we're working on that. It's just something that I wanted to make everyone aware of, because if you actually view the profiler output for both either this exercise or if you do this with your own code, right now that's kind of still a problem that needs to be fixed. I just wanted to give a little teaser for what we're going to talk about next time. Our next module will be presented by Max Katz, and it's going to involve the CUDA multiprocessing service, which is kind of a better solution in terms of performance. It's designed to concurrently map multiple MPI ranks onto a single GPU. So if you have just an MPI parallel application, MPS is a really good solution to use. Again, it would be used when each rank is too small to fill the GPU on its own. And on Summit, you can use the alloc flag GPU MPS when submitting a job to enable the multiprocess service. So Max is going to give an intro and to MPI and MPS in our next module. And then we're actually going to have a third module taught by Bob Cravella on CUDA debugging. So this is another thing that we get asked about a lot, just what debugging tools are there for GPU debugging and where do I start? How do I go about that? So that's what we have coming in the future. That's it for today. I will take any questions now, and our homework is actually I have the wrong link in here, but this should be homework 10. It's the same GitHub repository, but my link is wrong here. I'll fix that.
Okay, Sherry, can you please stop the recording?